Okay guys, so we're going to take a look deeper in this unit into logarithms, what they are, how they work. Back in grade 11, we introduced to you guys the idea of log and how we can use log to isolate for an unknown in the exponent. By the way, if anyone has headphones or cell phones out, those can just go away now, please. So we could use log to isolate for an exponent, but for grade 11, I was just like, just trust me for now. We can use it. We'll learn more about it in grade 12. So we'll talk about why that works and what a logarithm is, how it connects to exponentials, and we're going to be doing some more work with exponentials and things like that in this unit. So just as a little recap, in grade 11, we used the formula y equals a times b to the x for exponentials, where Keaton, can you just shut the back door for us there? Thank you. Where a represented the initial value, however much you started with. B was either your growth or decay factor, so things like doubling, tripling, we talked about half-life questions. Y was the future value, and then x would be the total number of growths or decays that you would have within the time limit. So you would take your total time and divide it by the growth or decay period. So let's just do a couple review questions here to get us back into exponentials and how these types of questions work. So we have an insect colony. It has a current population of 50 insects. Its population doubles every 3 days. What is the population after 12 days, and how long until the population reaches 25,600 insects? Okay, so we're going to use the formula above, y equals a times b to the x. What do we know about this so far? What can we fill in out of y, a, b, and x? Zach? A. Okay, and what's a? 50. Okay, initial value of insects or initial amount is 50 insects. Okay, what else do we know? The growth factor. Which is? Doubles every 3 days. Okay, so we know that b is 2 because it doubles. The every 3 days part, that's going to help us with x. X is sort of the things that have to do with time. So that means that after 12 days will also give us some information about x. So if my population doubles every 3 days and I have a total of 12 days, how many times by the end of that 12 days will my population have doubled? Matt? 4 times. So basically we calculate this by doing total time, which is 12 days, over the time for one growth to occur, which is 3 days. So that gives us 4 doublings that have happened over that total time. Okay, also we want to make sure that our units of measurement are both in the same unit of measurement when we talk about time. So here we have days and days. Okay, perfect. Let's plug it into the formula. Y equals a times b to the x. Okay, please guys use BEDMAS here. We're all in grade 12 at this point. I think we should know how to do this, but if we don't, BEDMAS means you have to do the exponent first and then you multiply in the 50. Okay, we're not doing 50 times 2 and then raising that to the exponent of 4. So be mindful of that. So what do we get here? Kenzie? 800, anyone else get this? 800 what? Insects. Be less specific, actually. Okay, so therefore, after 12 days, there would be 800 insects. Okay, is this starting to ring a bell from last year a little bit? All right, so that is like your very basic exponential growth type question. The follow-up to this question, which we introduced logarithms with last year, is how long will it be until the population reaches 25,600? So now we still have a population of 50 insects. It's still doubling every 3 days. But now I know the future value is 25,600. And I know a piece of x. I don't know the total time that it takes to reach 25,600, but I do know that it's happening every 3 days, doubling every 3 days. So I should expect, once I solve for time here, I should expect to get out my time in days, because I'm putting in a doubling period of 3 days. So I'll always get time out in the period or the same unit of measurement. Okay, so let's plug in what we know into y equals a times b to the x. All right, so here again, we want to be mindful about bed mass. I cannot multiply 50 times 2 because this has an exponent on it. What I would want to do is, if I'm trying to isolate for the t in the exponent there, is I will divide out that 50 to start, because I want to start moving everything away from the thing that I'm trying to solve for. So we'll divide out 50. I got 512. And there's a couple options for what we can do here. One of the options is we could guess and check, which would mean that I would try 2 to a bunch of different exponents until I get 512 from that, and then I would be able to solve for my exponent. Now, sometimes the time might not be a whole number, so that becomes a lot more challenging when time is something like a decimal. We want to have a definitive way of solving for this, regardless of whether time is a whole number or not. So what we used in grade 11 was called log, and for our purposes for right now, we know log can help us isolate for an exponent. And what I need to have in order to use log is I need to have the base and the exponent alone on one side. So that's where dividing out the 50 helped us with that. And then I can just go in and take the log of both sides. What I do to one side of the equation, I must do to the other. We're not using our calculators yet. Okay, and what we know of log is that right now we know log can help us by actually taking this exponent now and dropping it in front as a multiple. That's what log allows us to do. So we'll have the log of 512, and then I'm going to bring this t over 3 down as a multiple. Okay, that's a log rule, something that we're allowed to do with log. And then we will start to move things away from t from here on out. So I'm going to start by dividing out the log of 2. Okay, again, I'm still not using my calculator at this point. There's no need right now. So don't calculate all the way down. Wait until the end. So we have the log of 512 over the log of 2 equals t over 3. If I want to get t by itself, the opposite of dividing by 3 would be multiply by 3. So we'll multiply each side by 3. These will cancel. And now you can use your calculator. So I'm going to calculate t times the log of 512. If your calculator opens a bracket, you must close that bracket. That's an important piece. So let's highlight that. If my calculator opens a bracket here, I must close that bracket before I divide by log of 2. Otherwise, it's going to include the log of 2 inside the other logarithm, which we don't want to do. So 3 times log of 512, close the bracket if needed, divide by log 2. Let's see what we get. Okay, some of you guys have this button on your calculator. We don't want to use this button. We want to just find the regular log button on the calculator. Some of you guys just have like a regular log button that looks like this. This would be the button that you're looking for. Okay, what should we have gotten here? Sam, what'd you get? 27, right on. Okay, everyone else, I see heads nodding, that's good. 27 what? What's the unit of measurement? Days. Okay, good. Okay, so therefore it would take 27 days for the insect population to reach 25,600. Okay, and again, we know this is days because the original doubling period was in days. So if that's in days, this must also be in days. If you weren't able to get this on your calculator, I would be willing to bet that you did not close this bracket right here. Okay, so most of your calculators, raise your hand if your calculator opened a bracket there after you put in log. Yeah, so many of your calculators will do that. You just have to make sure you close it up. Okay, guys, super important for this unit, you need to have your own calculator and you need to be following along with what we're doing because this is kind of new for us, this like log function. Yes, we used this in grade 11, but there's going to be different stuff that we'll do with the log function. And you need to know how to use your own calculator. So please make sure, bring your calculator, follow along as we're working, and make sure that you know where these buttons are. If you don't, ask questions so that I can help you, okay? Okay, so one thing that we need to do in order to understand logarithms is we need to sort of go back to grade 9 for a couple minutes here, and we need to review the exponent laws because exponents are directly connected to logarithms. So let's just quickly review these exponent laws that we learned in grade 9. We have the product rule. So the product rule says when we multiply two like bases, we keep the base, and anyone know what we do with the exponents? Kenzie? Add the exponents. So keep the base, add the exponents. A plus B. So similarly, when we divide two like bases, we keep the base, and what do we do with the exponents here? Bella? Okay, so it will always be top minus bottom exponent. So keep the base, subtract the exponents. Okay, power rule. So when I have an exponent on an exponent, what do I do with the exponents to simplify? Sam? Okay, keep the base, and we'll do A times B. So multiply the exponents together. Negative exponent rule, we talked about this one in grade 11. Bella? Okay, so you will move, if you have a negative exponent, you will move this to the opposite side of the fraction. So if it's in the numerator, you will move it down into the denominator, then you can make the exponent positive. If it were in a denominator, you can also move it up to the numerator and make the exponent positive. So move it to the opposite side of the fraction. And exponent of 0, anything to the exponent of 0 is equal to, Clayton? 1. All right. So that will just give us a bit of a reminder for some base knowledge that we'll need for this unit that we'll touch on later. Okay, and we also need to recap what is an inverse function. So in grade 11, we talked about inverse functions. Just as a reminder, inverse functions are denoted using f, and it looks like a little exponent of -1. It's not an exponent, it's just a notation. And this notation means it's the inverse function of f at x. So we read this as f inverse of x. We can write that, I guess. F inverse of x, or at x, not an exponent. So the -1 is not an exponent. Okay, so sometimes we might be like tempted to use the negative exponent rule and say, oh, if I have f to the -1 of x, this is equal to 1 over f at x, but that's not true. Simply because this is just a notation that we use to indicate to the reader that we've found an inverse function. Okay? Inverse functions have the properties that they have opposite x and y coordinates. So basically this means if I sub in a value into my original function and I get some other value out, if I sub in that other value that I got out back into my inverse function, it should undo everything the original function has done and give me out what I started with. That's basically what this is saying. So the x and y coordinates of the inverse functions are swapped. So as an example, if I were to put in to my original function 5 and I get out 13, if I were to plug 13 into the inverse function, it should undo all of that and give me back out 5. So basically, as I said, the x's and y's are swapped in the original versus the inverse. Okay, and then graphically, what happens here is if I have a function f at x, so let's say this is f at x, the inverse function actually ends up reflecting over the line y equals x, which is this line that sort of goes diagonally across here, where all of the x and y's are equal. So negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4. I think that I've still got that on the right. Oh no, it should be here. So negative 5, negative 5. Oh no, that was right. Okay, so it's right along here. So this is the line y equals x, and if you imagine sort of putting your head on an angle here and closing the paper, that's the reflection line. So this would be f inverse of x here. And this will be true for all functions and their inverse. They will all be reflected over that diagonal line. Okay, I can generate this line y equals x, by the way, by simply just graphing all the points where x and y are equal. So 1, 1, 2, 2, 3, 3, 4, 4, and so on. So if you're not sure how to draw that, I'm just looking at where all of those values are sort of meeting up along the way. Okay, so last year we practiced with finding algebraically the inverse of a function. We did it with mostly like square root functions, quadratic functions. We did some linear functions. We're going to talk about how we would do this with an exponential function. So here is the process that we learned in grade 11 for how to find an inverse. The first thing that we typically do is, I'm just going to follow along, so I'll number these as I go, is we would replace any function notation with just the value y temporarily while we do this. So first step, replace f at x with y. Oops. Okay, second step, we swap the x and y's. And based on what we just reviewed about exponential functions, about inverse functions, we know that inverse functions have x's and y's that are opposite of one another or swapped. So we do this algebraically to find the inverse as well. So I'm going to switch any y for an x and any x for a y. And then we will go and we will try to get y by itself. Now, this is a little different from what we did in grade 11 because y is now in the exponent. But I know I can get an exponent down and in front as like a multiple if I use log, right? So we're going to take the log of both sides so that I can get that y down out of the exponent because I want to isolate for it if I'm trying to find the inverse. So log of both sides, what I do to one side, I must also do to the other. And then we will bring that y down in front as a multiple. I said this was like we parachute it down, right? Like parachute rule. Imagine it sort of going down in front. Okay, so I'm going to bring that y down. I think we can get y by itself now, right? I just have to divide out the log of 2. These will cancel. Y will be by itself. And now I have y equals the log of x over the log of 2. Now, there's one log rule that I'm going to introduce to you guys here. Which is, I will re-talk about this later in the unit, but for our purposes today, this is called the change of base formula. And it says if I have two logarithms with some value over some value, I can express this as a single logarithm by writing it like this. So it will be the log of the value on the bottom will become like a little subscript here. And then the value on the top will be the full value here. So we actually would state this as log base 2 of x. And don't worry too much about this right now, but this is the change of base formula. And that's just going to help us with understanding like kind of what's coming next here. Okay, we will talk more in depth about this a little bit later. And then last step, step number 4 says replace y with inverse notation. So f inverse at x is equal to log base 2 of x. That's how we would say that. Okay, so value down here becomes a little subscript. Value up here goes here. Maybe I'll put that in blue. Okay, so this is our inverse function. That's the final function here. And we're actually going to graph both of these below. So I'm just going to focus in here on 3 key pieces of information when we graph exponentials. And then we'll reverse those to get the 3 key pieces of information of the logarithmic function. So I've set out some x's for us here that I want to use for the 2 to the x function. What we're going to do to get our y's is just sub them into the 2 to the x function. So 2 to the 0 is equal to 1. Anything to the 0 is equal to 1. And 2 to the exponent 1 is equal to 2. Does anyone remember where the horizontal asymptote lies for any exponential function? All exponential functions have a horizontal asymptote. Kenzie? Just 1. Yep, it lies along the x-axis. What would be the equation of a line that lies along the x-axis? Bella? Y equals 0. Okay, so I have a horizontal asymptote along the line y equals 0. Can somebody tell me why is this called y equals 0 if it's on the x-axis? Why do we label that y equals 0? Keaton? What do you mean by y-intercept? Okay, so this is 0. So basically that means if I were to mark off every point on this line, you guys don't have to write this, but every point on this line has something in common. And that is that every point on this line has a y that's equal to 0. That's why we call a horizontal line like that, y equals the number that it cuts through. If I were to write it up here, this would be y equals 5, because every point on that line has different x coordinates, but all the y's are equal to 5. So that's why we say along the x-axis, y is equal to 0. That's why that's the way that we state a horizontal line. Okay, so let's plot this, 0, 1, 1, 2. If you wanted to, you could also add on here, like we know 2 to the 2 is 4, so you could add that point on there as well if you wanted to. And just as a recap, remember exponential functions usually start small and then they get really big really quickly. Or if they're decayed, they'll start big and get really small really quickly. So it should always be curving along your asymptote, and then it sort of grows off the other side here. Okay, and to get our key pieces of information for our inverse function, if you guys remember back from grade 11, all we really need to do is just swap the x and y's. So I don't need to know how to even calculate this in my calculator at this point or anything like that. All I'm going to do is these y's will become the new x's. And these x's, these x's, whoops, here we go. These x's will become my new y's. So this will be 0 and 1. Any guesses what happens to a horizontal asymptote? We didn't do this in grade 11. What would happen to a horizontal asymptote if I'm going to do an inverse function? Just guess. Doesn't have to be correct. Matt? It will become a vertical asymptote. So rather than having a horizontal asymptote, logarithms have a vertical asymptote, and it will be along the line x equals 0, or in other words, the y-axis. Okay, so I'm just going to pencil that in with a dotted line. That's the asymptote. And then we're going to plot our points here. So 1, 0, that's right here. It's okay if it's two separate functions, right? So it's okay that it's crossing over the other asymptote for the other function. And then 2, 1. And if you wanted to, we also graphed the point 2, 4, so we could graph the point 4, 2 if we wanted. You don't have to, but it's on there anyways. Okay, so here's our logarithmic function. Remember, it should be sort of like folded over that line there, right? It's reflected over the line y equals x. So it should look something like this, and it curves down toward the asymptote here. And we'll label that as f inverse. Actually, I got to move that over a little bit. Of log base 2 of x. Okay, so let's take a look at some of the properties here of the original function and of our inverse function. X-intercept for y equals 2 to the x. Bella? Correct, because on the x-axis there is an asymptote, so our graph will never touch that and it will never cross that. What about x-intercept for the logarithmic function? Keaton? 1, 0. It's right there. Okay, y-intercept for both of these. What are the y-intercepts? Sam? Okay. So 0, 1, that's where we cross the y-axis right here. And the other one does not cross the y-axis because there's an asymptote along the y-axis at x equals 0. So we would say none. Domain. So we're thinking back, we did a recap of this for polynomials, but we're thinking back to, we can do interval notation if you guys want, or inequality notation. So left to right for the blue function. Are there any restrictions left to right for the blue function? Okay, so let's say negative infinity to positive infinity for domain here. We'll do range as well for the blue function. So 2 to the x, any restrictions on the bottom to the top here of the blue function? Michael? Yeah, so that would be the other option. You can also just write for domain, x is an element of real numbers. That would be the other notation. Okay, so restrictions on the range. Is there a restriction on the bottom boundary or top boundary at all for the blue function? Bella? Okay, so notice that we do not go into the negative section of this graph. There's an asymptote along, so y is greater than 0, right? Yeah. So the y's are not equal to 0 because my graph doesn't touch the asymptote, but they are higher than 0. So I must say above 0. So one way to say this is 0 to infinity, or if you would like, you can also say y is an element of real numbers such that y is greater than 0. Okay, so either notation is fine. Okay, let's talk about domain and range for the red function. Any restrictions on the left and right boundaries of the red function? Oops. Okay, so if we look at the red function, I'm seeing the red function goes forever toward the right. Does it go forever toward the left? There is a boundary on this, right, along the line x equals 0. So how do I state this? Sam? Okay. Or the other option is I can say x is an element of real numbers such that x is greater than 0. Okay, and the range for the red function. Is there any bottom boundary? Is there any top boundary where this will stop going upward? I think this goes down forever. We can pretty clearly see that. And then we have to imagine if this continues, it's just going to continue getting higher and higher and higher. So no restrictions on the range. So we can either say negative infinity to infinity, or we can say just all real numbers. Okay, and then we wrote our asymptotes above. So the asymptote on the blue function was the line y equals 0, and then on the red function, the logarithmic function was x equals 0. Okay, so a couple things that you should notice here. The domain and the range of the original function and the inverse function are sort of like swapped, right? Like here, the range became the domain of the logarithmic function, and here the domain sort of like became the range. So we switched the x's and y's in these, obviously, but the domain and range get swapped. Also, the intercept sort of gets swapped as well. So in one of them, there's no x-intercept, but in the other one, there's no y-intercept. And then, of course, these get swapped as well. So these are going to be opposite of one another. All right, so let's talk a little bit about like what is a logarithmic function, how do some of these things work, and we'll go from there. So the logarithmic function is the inverse of the exponential function with the same base. So above we took a look at the exponential function with base 2 to the x, but of course we know we can have any exponential function with any base, right? So if I had 3 to the x, then the logarithm with base 3 will be the inverse of the exponential with 3 to the x. Okay, so as I said, we would have the logarithm of the base of x, and that will be the inverse of b to the x, whatever that b is. Okay, so looking at our domain above, this function will only be defined for x's that are greater than 0. So it's only defined when x is greater than 0, meaning we can't have negative values, or we can't even have 0 in for x. Okay, and in this notation, b is the, x is the exponent to which b, the base, must be raised to give the value of y. X and y are swapped. Y is the exponent to which the base must be raised to give the value of x. Yes. So the answer to a logarithm is an exponent. And that's why we where that connection comes in as to why we can use logarithms to help us isolate for exponents, because when I put log into my calculator, the answer is actually giving me out an exponent to which the base must be raised to get this value right here. Okay, so the solution to a logarithm is always an exponent, gives me an answer of an exponent. And Because of that reason, logarithms are very useful for solving unknown variables when they are in exponents. Okay, and what we've been using so far from grade 11 is what we call the common logarithm. And it's a logarithm with base 10. And so common logarithms are logarithms with base 10. When we press the log button in our calculator, when it's just like the regular log button, so on my calculator, for instance, this Casio calculator with the burgundy type buttons, I can type in log, and when I type in log, one thing that's understood about that is that I'm calculating what is called a base 10 logarithm. This is the common logarithm. There's lots of base 10 systems that we have in real life, especially like in science and chemistry. We talk about things like decibels, pH, all kinds of different things as base 10 systems, which is partially why we have a common logarithm of base 10. Okay, so just like when I have x, what do we understand about an exponent on x here if it's not written? What's the exponent on just a single x? 1. So we understand if I write x, that the exponent on that is 1. We also understand that if I were to write a square root, sometimes we write numbers out front of square roots, like cube root, fourth root, and so on. But if I just write a regular square root, we understand that there is a 2 in front of that without writing the 2. And it's the same for logarithms. So for the common logarithm, if I just have log of a number or log of x or whatever, it is understood that that thing is base 10, and we don't write the base of 10. Otherwise, if it's any other base, we would actually indicate the base with a little subscript. Okay? So this would never actually really be written. We would always write it as log of x and understand that there's an understood subscript of 10 there. Okay, so we just need to learn some of the basics today of like how we write these things and how we switch between the forms and things like this. So if I were to switch between exponential and logarithmic form, we would always sort of be switching in this format. So x will be equal to, so x, the answer is the exponent. The base is always the base that we have here. And the answer to the exponential will be what we would put into our logarithm here. So just in this notation, that's how we would swap. Exponent becomes the answer, base becomes the base of the logarithm, and the answer is what we would put into the logarithm. These are sort of like the inverted forms of one another. Okay, and then if I want to switch back into exponential format, if I have this, I will have so remember this is the exponent. This will be my answer, so x would be equal to the base b to the exponent. So the answer to the logarithm is the exponent. Okay, so that's sort of how we swap between these two things. So let's look at a few examples if we were to rewrite in exponential or logarithmic form. So 81 equals 3 to the 4. The 4 is the answer. Okay, so I would write 4 equals log base is 3, so that becomes a little subscript here. And the answer is what we would take the log of. Basically, if I write something like this, I am giving the answer to what 3 must be raised to get 81. So the question of the logarithm here, if I didn't know this, if I were just calculating this, it's asking me 3 raised to what exponent is 81. And that's what the logarithm gives me out. It gives me out 4 because 3 to the 4 equals 81. So that's how we would rewrite it. Okay, does someone want to do B for us? Try it out. Also, you can have this in either order, like log base 3 of 81 equals 4, or vice versa. Who can try B for us? Zach?
It would be like 4 equals log h.
So it will be log of h, and what is?
And then the x and the
So that the x will be the subscript. So we say this, we read this as log base x of h. So we're basically saying x to the exponent 4 should give us back this value. Okay. How about this one? Who wants to try this one? Sam, you want to do this one? It's the same. It's the same as before. So exponent, what's the exponent? That will be the answer. What's the base? And then I need the subscript. Okay, so log base 8 of 64. Okay, whatever the base is here becomes the new base of your logarithm, right? Whatever the exponent is, that becomes the answer to the logarithm. And the answer of your exponential expression always becomes what we're taking the log of inside the logarithm there. Okay, so log base 8 of 64. Basically, we're saying 8 to the exponent of 2 should equal 1 over 64. Okay, how about this one? Keaton.
Would that be 4 equals log base 10?
Okay. Does someone want to add to this? Bella? This is the common logarithm, so I will only write log of 10,000, and the base 10 is understood. So no need when your base is 10 to write the base of 10 there. Okay, and then the last one, we might want to do one little change first before we begin switching. How do I write a square root as an exponent? Taking this back to second unit of grade 11. Clayton?
Oh, wait, I don't know.
Okay. Kenzie? 9 to the exponent half. So another way to write a square root would be exponent of a half. That's because I have a 2 out here and a 1 out here. So if you guys remember back from grade 11, we do 9 to the 1 over whatever the root is. So in this case, it's a 1, or sorry, a 2. Okay, so how do I switch this into logarithmic form then? Zerwa?
Oh, no. I have a question. Why
Okay.
can't you just do 3 squared?
Well, we would sort of be changing the equation then, right? So we're changing the logarithmic statement. So I want a logarithmic statement for this exactly. If I square both sides, now I'm changing what the logarithmic statement will be. I mean, it's still equivalent, but
You're not changing it, you're just solving it because the square root is 9.
I don't need to solve it though, right? It's just a statement. It's not an equation. Okay. Surwa.
So what is this used for?
We'll do like a ton of applications, but logarithms like are very useful, like I said, in chemistry and science. So like thinking about like pHs, decibels, all of that types of stuff. So yes, it will. This is useful in the real world. Okay, so who can do this for me? Back to this one. Serena.
It'll be 1/2 equals log 9
3. Good. So log base 9 of 3. So basically I'm saying 9 must be raised to the exponent half to give me 3. Right? Okay. Oh my goodness. Yes, we will take 60-second brain break. You can check your phones too.
They're watching Netflix.
All right. Okay, so we're going to write each equation in exponential form, and for b, we're going to graph both versions of the function. So who can switch this one into exponential form? So basically the opposite of what we did above. Rebecca?
32.
36?
What?
I'm at 36 is equal to 2 with the exponent 6.
Is 2 to the 6 equal to 36? 6 to the 2. So the base of the logarithm becomes the same base here. This is the exponent, right? The answer to the logarithm is the exponent. Okay, so obviously, guys, if you have numbers here, this should make sense, right? 36 is equal to 6 squared. So perfect. Okay, how do I switch this into exponential form? Bella? That's a good question. Where does the 10 come from?
Understood.
It's the common logarithm. Common log.
So if I don't see a base here, I understand that there is a base of 10. Okay?
Wait, but what about where do we put the log? Oh, I see it. Am I what? What did you just say? What?
Okay, so this question asks me to graph the logarithmic function. And for the logarithmic function, we're going to use just sort of like a similar format to what we found up here. So when this was base of 2, we had the point 1, 0. That's going to remain the same because 0 and to any base, if I were to look at the original function, 2 to the x, 2 to the 0 is always 1. So it's always going to be the opposite in the logarithm as well. So every logarithm will have this point, unless it's like shifted or something like that. And then the base will always pair with 1 here. So because the base is 2 here, I have the point 2, 1. So when we were graphing the exponential version of this, of course, we put 2 to the exponent 1, and we got back 2. If I were graphing the original version of log base 10 to the x, I would be graphing the function y equals 10 to the x. So if I were looking at that, if I choose 0 and 1 for x, I plug in 0 here, I get 1. I plug in 1, I get 10. Okay, so I'm not saying that this is the same as this. I'm just saying this is the inverse function of y equals log to the x. This is just the way we rewrite it in exponential format. So this will help us get the points for the logarithmic function, right? Because I'll just swap them. And then, of course, we know that this has a horizontal asymptote of y equals 0. And if I swap that, it becomes a vertical asymptote at x equals 0. This is the one that I'm going to graph, because that's what the question asks me to do. It says graph the original function. So you're going to pencil in your vertical asymptote, and then just graph your 2 points, 1, 0, and 10, 1. Should curve around toward your asymptote here. And then through that point there. Okay, any questions on this before we move to the last page here? Okay, last part is pretty quick. I'm just going to teach you how logarithms, how we can evaluate these, and this is going to be without a calculator, so no calculators needed. Other than if you need to like guess and check, maybe you can use a calculator for that. But I'm going to show you two ways that we can do this. This doesn't always work. This only works if your answer is a whole number. But it just helps us with our understanding of logarithms a little bit better. So this question is asking me 5 must be raised to what exponent to equal 125? So I know that if my bases are the same, then the exponents must also be equal. So the goal with this rule is express this in exponential form. So we're saying y will be the exponent, 5 will be the base, and that should be equal to 125. And then if I can figure out what 125 is as a base of 5, I will figure out what y is equal to. So 5 raised to what exponent would give me back 125? Clayton? 3. So 5 cubed, which means that based on this rule above, if the bases are equal, then the exponents must also be equal. So therefore, y must be equal to 3. So the logarithm is equal to 3. Okay, so you can create common bases, and then the exponents have to be equal. You might have to just guess and check for exponents of what exponent of on 5 would give you 125. So I'm just expressing 125 as a base of 5. Okay, the other rule is if I can figure out, so this is actually similar, but it's just a different format. If I can create the same base that I have of my logarithm with this number, then my whole logarithm will just be whatever I get as this exponent. So if I can figure out what is 16 expressed as a base of 2. So 2 to what exponent equals 16? Sam? 4. Okay, so if I can write it like this rule says that if I can express these with a common base right here, this one here and this here, because 2 to the 4 is equal to 16, that this whole logarithm will then just be equal to this single value right here, which is 4. And I know that this is true because this logarithm is asking me 2 to what exponent equals 16. That's the answer to the logarithm. So 2 to the exponent 4 equals 16. So log base 2 of 16 equals 4. Okay? So that's always the question. What exponent must I raise the base to get the value inside the logarithm there? So what exponent must I raise 2 to get 16? What exponent must I raise 5 to get 125? I must raise it to 3. Okay, so if we were to do these are slightly different because there's fractions in here. If I have a fraction, all it means is my exponent answer must be negative if I get a fraction. So I like to think of this. What is log of 1,000? And then if I can figure out what that is, then I just make it negative, and that's the answer to this one, right? So if I were to try to solve what is log of 1,000, this is base 10. I'm asking myself 10 raised to what exponent equals 1,000? Matt? 10 raised to the exponent negative 100? Sam? Yeah, 10 cubed. 10 times 10 times 10. Close with the 100, but you're thinking multiply. Okay, so if I have 1 over 1,000 then, it won't be 3, it will be negative 3. So I can express this sort of like this. 10 to the y equals 1 over 1,000. And then if I want to express 1 over 1,000 as a base of 10, I would write this as like 10 to the negative 3. And that means that y equals negative 3. Okay, and then similarly for this, if we think of this instead, then I'll just make the exponent negative because I have the fraction there, right? So 3 raised to what exponent equals 81? That's the question. Bella? Yeah, so 3 to the exponent 4 equals 81. So because I have 1 over 81, that tells me that my logarithm must be equal to negative 4. Okay? Because 3 to the negative 4 equals 1 over 81. Okay? So that's your answer to your logarithm. Okay, so I want to try some work with logarithms before we leave today. Let me just stop the recording here.